Hi everyone, welcome to our project presentation. My name is Bhavani and I'm here with my teammate Anu Anand. Today we will walk you through our project on predictive modeling for dynamic pricing. This involves sorting and selecting data, feature engineering, and training machine learning models like linear regression, random forest, and XGBoost.
Data pre-processing and selection. Let's start by explaining how we pre-processed and selected the dataset. We cleaned the dataset by finding outliers and removing them. We did data imputation for price by adding the median. Also, we removed duplicates and dropped the columns which we thought were not necessary for building the model. Our dataset is very huge, which contains about 600,000 records, which makes training of the model very difficult. Therefore, we concise the dataset by sorting the data based on the price column, selected records from both ends of the dataset, and reset the index for consistency. We saved the final dataset as sorted underscore selected underscore data.csv and printed its shape and a preview.
Next, we prepared the dataset by encoding categorical columns like source, destination, and cap type using label encoder. This is necessary because machine learning models typically work with numerical data. We also define numerical features that contribute to our target variable's price. Let's explore the insights of our right data. We have visualized four key aspects: the right counts by service type, the average price by service, and the impact of weather on the right prices. Let me walk you through the first visualization. The plot shows the ride counts for Uber and Lyft services. As you can see, Uber rides are more popular than Lyft rides. Understanding this distribution helps us see which service is utilized more often in our dataset. Next, we analyze the average ride price for each service type. The bar chart here indicates Lyft rides are slightly more expensive on average compared to Uber. This could be due to differences in service offerings or pricing models.
Impact of surge multiplier on prices. The box plot shows the impact of surge multiplier on ride prices, with only one value indicating no surge pricing is applied. Most ride prices fall between $10 and $30, with a median slightly above $20. A single outlier priced around $80 suggests unusual factors like long distance trip or specific service type. The data reveals that without surge pricing, ride costs are fairly predictable, but price variations still occur due to other influencers. Further analysis could explore higher surge multipliers of variables like distance, service type, or weather to provide deeper insights. Impact of weather on prices. Lastly, we explored the impact of weather conditions on ride prices. The box plot shows the price distribution for weather conditions such as clear, rainy, or snowy. We can observe that prices are generally higher during certain weather conditions like rain or snow, likely due to the increased demand or reduced availability. These visualizations provide valuable insights into user preferences and external factors influencing ride prices. Such findings can guide pricing strategies and service optimizations for ride sharing companies.
We used Folium to create an interactive map showing the spatial distribution of Uber and Lyft rides in Boston. This map helps us visualize ride patterns across the city. We concentrated the map on Boston, added a marker cluster for grouping rides, and sampled 10,000 records to ensure the map loads efficiently.
Finally, the map is saved as ride_map.html. When opened in browser, it provides an interactive view allowing us to explore ride patterns easily. We split the data into training and testing using an 80-20 split. This ensures our models are trained on one part of the data and evaluated on unseen data for unbiased performance metrics.
Linear regression. We Linear regression is our first model. It's simple but effective in understanding relationships between features and the target variables. Next, we used random forest, an assembled model that combines multiple decision trees to improve prediction and reduce overfitting. The next model we build is XGBoost, a powerful gradient boosting algorithm that excels in handling large datasets and providing accurate predictions. Going forward, we did hyperparameter tuning with randomized search CV. Here is how we tune the hyperparameter parameters for the random forest model using randomized search CV. We defined a parameter grid including the number of trees, maximum depth, and minimum samples required at splits and leaves. Randomized search CV sample 50 parameters combinations across 5 folds across validation, optimizing for RMSE.
For XGBoost, we created a parameter grid covering learning rate, max depth, subsampling, and tree features. Randomized search CV performed 50 iterations to identify the best configuration. The evaluation metric remained RMSE as it penalizes large errors effectively. Among the three models, XGBoost demonstrated the best performance with the lowest MSE of 89.65 and the highest R squared of 0.53. This indicates that XGBoost is the most accurate and reliable model for predicting dynamic pricing in the dataset, effectively capturing the variability in the data compared to linear regression and random forest. Thank you for watching our walkthrough. Please feel free to ask questions or share your feedback.